Dinitrogen. The next topic is dinitrogen, the preparation of the dinitrogen. How will you prepare the dinitrogen? Dinitrogen means N2. See, usually the dinitrogen produced in commercially by the liquefaction of the fractional distillation of air. That is, the liquid nitrogen, they have a 77.2 boiling point. That is 77.2 Kelvin having a boiling point. So it distill out leaving behind liquid oxygen. That is, the boiling point is 90 Kelvin. The dinitrogen can be prepared by treating of an aqueous solution of ammonium chloride with sodium nitrate. For example, see ammonium chloride NH4Cl, that is aqueous solution of the ammonium chloride treatment with sodium nitrate. This is also an aqueous form. To form nitrogen gas, water molecule, and the sodium chloride salt. Sodium chloride salt in aqueous form. This here the small amount of the impurities like nitrogen monoxide and the HNO3 are also formed. These impurities can be removed by the passing of the gas through the aqueous sulfuric acid containing the potassium dichromate. So it can also obtained with the thermal decomposition of the ammonium dichromate. See, for example, ammonium dichromate NH4 twice Cr2O7 on heating to obtain nitrogen, just pure nitrogen and chromium oxide. Very pure nitrogen, that is, can be obtained with the thermal decomposition of the sodium or barium acid. For example, barium acid, BaN3 twice. So this is the acid to form barium and nitrogen. See, that is the properties of dinitrogen. So properties of the dinitrogens mean its dinitrogen is a colorless, odorless, tasteless and non-toxic gas. So nitrogen having two isotopes, that's isotope is N14 and N15. See, it is very low solubility in water, so on the low freezing point and the boiling points. The dinitrogen is rather inert at room temperature because of the high bond enthalpy of N triple bond N. So they have a triple bond. So reactivity, however, increases rapidly with the rise in temperature. When rise the temperature, reaction also increases. So at high temperature, they directly combines with some metals to form predominantly ionic nitrates with non-metals. That is coal and nitrate like this. For example, 6 moles of lithium react with nitrogen to produce on heating to form lithium nitride. 3 moles of magnesium react with nitrogen on heating to produce magnesium nitrate, Mg3N2. So these are the example reactions. It combines with the hydrogen at about 773 Kelvin speed to form ammonia. This preparation of ammonia. Nitrogen gas react with 3 moles of hydrogen gas at 773 Kelvin temperature to form ammonia gas. So this the bond formation, that is this is called the Haber process. Here the dinitrogen combined with the dioxygen only at very high temperature, that is nearly 2000 Kelvin, form nitric oxide. That is nitrogen monoxide N2 react with oxygen on heating to form nitrogen monoxide gas. Then the uses of nitrogen. Uses of nitrogen: manufactures of ammonia in biological material like refrigerant, food industries, that is food items, in cryosurgeries like this, where it is used. Then ammonia. Ammonia prepared by, see the preparation of ammonia. Ammonia is present in small quantities in air and soil, where it is formed by the decay of nitrogenous organic matter like urea. What is the formula of urea? Means there is NH2CO NH2 react with, that is water, is dissolved in water to form, that is ammonium carbonate, NH4 twice CO3. Then again it gives ammonia, water and the carbon dioxide gas. See, on a small scale, ammonia obtained by the ammonium salt, which decomposes when treated with caustic soda or calcium hydroxide. For example, NH4Cl, ammonium chloride, react with calcium hydroxide, CaOH twice, gives ammonia and calcium chloride. The main product is ammonia and calcium chloride. Similarly, ammonium sulphate. The ammonium sulphate treated with caustic soda, 2 moles of the NaOH to form ammonia, and sodium sulphate. So in large scale, that is well known process, Haber process, ammonia manufactured by Haber process, Haber's process. That is nitrogen gas react with hydrogen gas, 2 moles of NH3 gas. Here the delta H formation, standard formation, that is minus 446.1 kilojoule per mole. With this Le Chatelier principle, high pressure would favor the formation of ammonia. In optimum condition for the production of ammonia, pressure of nearly, that is 200 into 10 power 5 Pascal, about 200 atmospheric pressure. The temperature nearly 700 Kelvin. So here the use of catalysts such as iron oxide with a small amount of potassium oxide, superoxide, that is, and aluminum oxide to increase the rate of the reaction. So here this is the preparation process of ammonia. Then the properties of ammonia. The properties of ammonia is a colorless gas with a pungent odor, and the structure like this. The structure like this. Here the NH bond length is 101.7 picometer, 101.7 picometer, and the bond angle is 107.8 degree. So, and it contains one lone pair of electrons also. Here the freezing and boiling points are, the freezing point is 198.4 Kelvin and the boiling point is 239.7 Kelvin. So this is boiling point and this is the freezing point. In the solid and liquid states is associated through the hydrogen bond, as the case of the water, and that accounts for its the higher melting and the boiling points are then expected on the basis of the molecular mass. Here the ammonia molecule is the structure is a trigonal pyramidal. The structure trigonal pyramidal. The 3 bond pairs and 1 lone pair. This is 3 bond pair and 1 lone pair electrons are there. So ammonia gases are highly soluble in water. The aqueous solution weakly basic due to the formations of the hydroxide ion. So NH3 when react with water, that is insoluble in water, to form the ammonium ion NH4 plus ammonium ion and the OH minus. So both are aqueous state. So it forms that ammonium salt with acid, example ammonium chloride, ammonium sulphate, so etc. See, as a weak base, precipitate hydroxides of many metals form their salt and solution. Example, zinc sulphate. Taking of the zinc sulphate, aqueous solution of zinc sulphate react with the aqueous solution of ammonium hydroxide to form aqueous solution of zinc hydroxide. This is a solid form precipitate. This is the white precipitate, and ammonium sulphate aqueous solution, that is aqueous form of the ammonium sulphate solution. Then react with, that is ferric chloride. Ferric chloride react with the ammonium hydroxide, and that is both are aqueous solution to form ferric oxide brown precipitate Fe2O3 and X moles of the water molecule, brown precipitate of solid form, then ammonium chloride NH4Cl. This is the brown precipitate, and this is white precipitate. Here the nitrogen having lone pair of electron, so NH3 having lone pair of electron, so that it act as a Lewis base, that is ammonia molecules makes it a Lewis base. So it donates the electron pair from linkage of metal with metal ions and the formation of such complex compounds like Cu2 plus copper sulphate, any aqueous solution of copper sulphate that react with ammonia, aqueous ammonia, to form a complex, this Cu NH3 4 times 2 plus. So this is a deep blue precipitate. Then this is a blue precipitate. It comes a deep blue precipitate. This is a complex, formed a complex. Similarly, react with the silver chloride, aqueous solution of any silver compound, that is colorless compound, to form a silver chloride solid, white precipitate. Then the silver chloride react with ammonia molecule, aqueous solution of ammonia, to form a colorless complex, that is Ag NH3 twice Cl. So this is a colorless complex. So this is a white precipitate. Then uses of ammonia, where it is used means there is various nitrogenous reaction, that is and fertilizers industries for ammonium nitrate, urea, ammonium phosphate and ammonium sulphate, like this. So and manufacturers of some inorganic nitrogen compounds, and that is preparation of there is one of being the nitric acid, liquid ammonia. There is a liquid ammonia used as a refrigerant. So many uses are there. Then oxides of nitrogen. So oxides of nitrogen. What are the possible oxides of the nitrogen? Means here the N2O, the nitrogen 1 oxide or dinitrogen oxide. So here the oxidation state of the nitrogen is +1, and the common methods of preparation is NH4 NO3 and heating, that is ammonium nitrate and heating, to produce N2O and H2O. So it is the physical property is a colorless gas and neutral. Then the nitrogen monoxide or nitrogen 2 oxide. The oxidation status +2, and the preparation method is 2 moles of sodium nitrite NaNO2 react with ferrous sulfate and sulfuric acid to produce ferric sulfate and sodium hydrogen sulfate H2O and nitrogen monoxide. This is also colorless gas and neutral molecule. Then dinitrogen trioxide or nitrogen 3 oxide, that is N2O3. Here the oxidation status +3 for this nitrogen, and the preparation reaction is 2 moles of nitrogen monoxide react with nitrogen N2O4. The temperature range is 250 Kelvin to forms 2 moles of N2O3. This is blue solid in acidic. You said this is acidic. The above two is neutral. This is acidic. Then nitrogen dioxide NO2. Here the oxidation status +4. The preparation method is lead nitrate. React this lead nitrate on heating 673 Kelvin temperature to form 4 moles of NO2 and lead oxide 2 PbO plus O2. This is brown gas and acidic in nature. Brown gas, acidic. Then dinitrogen tetroxide N2O4. The dinitrogen tetroxide is the oxidation state here also the +4, and the reaction, the preparation reaction 2 moles of nitrogen dioxide and cooling, the reverse reaction on heating. In cooling you will be getting that is N2O4, and the colorless solid liquid, both possibilities are there. Then acidic in nature. Then dinitrogen pentoxide and nitrogen 5 oxide N2O5. Here the oxidation is +5 oxidation state, and the preparation reaction is nitric acid, that is 4 moles of nitric acid react with the phosphorus pentoxide, dimer form of the phosphorus pentoxide P4O10 to form phosphorus acid, and the dinitrogen pentoxide is formed. Here the colorless solid and act as a acidic nature. Here the Lewis these are the oxides of nitrogen examples. Then nitric acid. Nitric acid. Here the nitrogen forms the oxo acid such as hyponitrous acid H2N2O2 and nitrous acid HNO2, nitrous acid and nitric acid. See, among them here the nitric acid HNO3, this is the nitric acid. This is the most important compound. Here the preparation of the nitric acid, how will you prepare? The well known method, that is called Oswald process, that is a large scale. It's a small scale. For example, in laboratory preparation, sodium nitrate react with the sulfuric acid to produce sodium hydrogen sulfate and HNO3. In large scale, usually using the Oswald process, this method based on the catalytic oxidation of the ammonia in the atmospheric oxygen. For example, 4 moles of the ammonia gas react with, that is 5 moles of oxygen gas. The using of the catalyst is platinum or ruthenium, that is gang catalyst, platinum or ruthenium, up to 500 Kelvin 9 bar. So to form nitrogen monoxide gas and water, 6 moles of water gas. Here the nitric oxide is formed, combines with the oxygen to giving NO2. So here the nitrogen monoxide, there is 2 moles of nitrogen monoxide react with the oxygen to produce the 2 moles of the nitrogen dioxide gas. Here the nitrogen dioxide formed dissolved in water giving nitric acid. So here 3 moles of the nitrogen dioxide gas dissolved in water to produce 2 moles of nitric acid and the nitrogen monoxide gas. So here the nitrogen monoxide formed by the recycled and the aqueous solution of HNO3 can be concentrated by the distillation up to approximately 68% of purity by mass. So further the concentration to 98% can be achieved by the dehydration with the concentrated sulfuric acid. Then the properties of nitric acid. The properties of nitric acid, mainly the structures. The structure of nitric acid, the HNO3. Nitrogen, oxygen and hydrogen. Here the OH bond, this OH bond length is 96 picometer and this bond angle is 102 degree, and nitrogen oxygen, this nitrogen oxygen bond length is 140.6 picometer and this oxygen nitrogen bond is 121 picometer. So here the bond angle is, this bond angle is 130 degree. This is a colorless liquid. The freezing point is 231.4 Kelvin and the boiling point is 355.6 Kelvin. So the laboratory's grade nitric acid contains there is 68% of the nitric acid by mass, and the specific gravity is 1.504 the gravity. So the gaseous status nitric acid exists a planar molecular with the structure. See here the planar, the molecular structure. So the nitric acid behaves a strong acid, use hydronium and the nitrate ion. HNO3, aqueous solution of HNO3 to produce, that is hydronium ion and nitrate ion. So this concentrated nitric acid is a strong oxidizing agent also. It attacks most metals except noble metals such as gold, platinum, like this. This product of oxidation depends upon the concentration of the acid, the temperature and the nature of the material undergoing the oxidation. For example, 3 moles of the copper react with the diluted nitric acid, 8 moles of HNO3 diluted nitric acid to form copper nitrate, 3 moles of CuNO3 twice and 2 moles of NO, nitrogen monoxide, and 4 moles of water molecule. This using of dilute, this is a dilute form, and suppose if you use the concentrated form, this means Cu react with 4 moles is enough. 4 moles of HNO3, that is concentrate, to produce zinc, that is react with, to form copper nitrate, NO3 twice. Here the byproduct only changes, that is nitrogen monoxide above first reaction, here the nitrogen dioxide and the water molecule. When react with the zinc, the dilute nitric acid and the concentrate nitric acid to give zinc nitrate. These are the reactant, that is zinc produce zinc nitrate, and this is for dilute reaction to produce like this. Here dinitrogen oxide and here nitrogen dioxide. Only using of that concentration and the dilution, that is the difference you are getting, that different oxide form. Some metals like chromium, aluminum do not dissolve in concentrated nitric acid because the formation of the passive film of oxide and the sulfate. So the concentrated nitric acid also oxidizes the non-metals and the compounds. So iodine is oxidizes to iodic acid, carbon to carbon dioxide, sulfur to sulfuric acid, phosphorus to phosphoric acid. So you can see here the reaction. Reaction of iodine, 10 moles of HNO3 to form the iodic acid, HiO3, and nitrogen dioxide, and then react with carbon to form a carbon dioxide, HNO3, to form carbon dioxide and the nitrogen dioxide. Sulfur, react with the sulfur, that is 48 moles of HNO3 to form sulfuric acid, 8 moles of sulfuric acid and 48 moles of nitrogen dioxide and 16 moles of water. React with phosphorus, 20 moles of HNO3, that is nitric acid, to produce phosphoric acid, H3PO4, 20 moles of nitrogen dioxide and 4 moles of water. So these are the reagents. Here the main test for nitrate, presence of the nitrate, is a very common test, familiar test also, brown ring test. So the brown ring test performed, that is nitrates depends on the ability of that is Fe2 plus to reduce nitrates to nitric acid, which react with this Fe2 plus, that is ferrous sulfate, to form a brown colored complex. So this test usually carried out by the adding of dilute ferrous sulfate, that is freshly prepared ferrous sulfate solution that containing nitrate ion, and then carefully adding of concentrated sulfuric acid along the sides of the test tube to form a ring. That is, the brown ring is the interface between the solution and sulfuric acid. Layers indicate the presence of nitrate ions in the solution. So the reaction is NO3 minus 3 Fe2 plus. Here the freshly prepared ferrous sulfate only using. That's only gives a better result, because the freshly prepared ferrous sulfate, suppose already prepared, means converts to ferric. So that's why we are using always freshly prepared ferrous sulfate solution. Then Fe3 plus 2H2O. Then the brown precipitate like FeH2O 6 times 2 plus NO, yes, it is form a complex, that is brown color complex, FeH2O 5 times NO 2 plus H2O. So this is the nitric acid properties. Then uses of the nitric acid in fertilizer industries, in uses in explosives and pyrotechnics, then preparation of the nitroglycerin, trinitotoluene, and other organic nitro compounds. So here the major uses of the nitric acid, pickling of the stainless steel, etchings of metals, and as in oxidizers in rocket fuels. So many uses are there. The next we will discuss the next class. Thank you.